Alright, today we're going to cover section 5.5, which is just properties of definite integrals. We're just going to go over a few different properties and how to use those in this section. It's somewhat user-friendly, so that should be good news to you. This is the first theorem, 5.21. The definite integral can be just evaluated as c times b minus a. And this visual over here really helps to bring that to light, because if this was our equation, y equals c, okay, the area under this curve, which is defined by the definite integral, will be the same thing as your height times your base here, which of course that base is b minus a, so then we can see where those are equal. And we're able to apply that theorem. So let's see an example of this. So if I were to work this, then first of all we'll just have c is 4 times our b, our upper limit is 5 minus, and then our a is our lower limit, which is a -2, which that would just give us 4 times 5 plus 2, which is 7, so we would get 28 units square as the area, but the evaluation of this integral is just going to be 28. Whoops. Alright, our next theorem is going to be 5.22, and if f is integrable on a to b and c is any real number, basically all this is saying is we can pull the c out front, and we did that same thing a lot of times when we work with derivatives as well, and that's something we've been doing, so this should be very familiar to you. Basically it just means if I'm given this particular integral, I can pull the 5 out, evaluate this, which the antiderivative is just x, evaluate it from -1 to 1, multiply the answer times 5. So, and always just take a few minutes to pause these if I move too quickly, and make sure and give yourself time to write the theorems down. Alright, our next one is theorem 5.23, and this should look familiar to you as well. Just if you have the integral of f of x plus g of x dx, then you can basically break these apart into individuals and do the integral of f of x dx, get that answer, and the integral of this, get that answer, and then add them together. And likewise with subtraction. So I'll give you a few minutes to write that down, and then we'll look at an example. Okay, we're given some integrals with a value here. Now in the next section, 5.6, we're going to be able to evaluate these on our own, but for this particular lesson and these properties, they give us this information. So they give us this information, and they ask us to use that to evaluate this particular integral using our properties. So the first thing we're going to do is break this one apart. So we'll say, let me do it in a different color. So we'll say that equals the integral from 1 to 4 of the first term, which is 3x squared dx, plus the second term. So we can break these apart into individual. And then using our other property, what can we do with this 3? Right, because up here we know x squared dx and we know x dx. So let's bring the 3 out front. And this one I'm just going to leave it alone. Now we can see that this was what was given to us up there, so we can just plug in, we'll say 3 times 21, because this information was given to me and it fits the format, so I'm going to say 21 plus, now I could bring the 5 out and I can evaluate that, or I can use my formula for the very first theorem we worked with, 5 times b minus a, right? Our c, this is c times b minus a. You have some options here. Choose whichever one you prefer. 3 times 21 is going to be 63, plus 5 times 3 is 15. So we would evaluate this to get 78. Alright, our next theorem is going to be 5.24. And if you want to go through the extra step and go ahead and write down theorem 5.25 out of your textbook, you can, but they're very similar based on the same concept. So we're going to focus on 5.24, and also the image of it helps to see. And basically this theorem is just saying the area under the curve from A to C is this, and the area under the curve from C to B is this region. So if I added them together and did the area, it's going to be equal to the area from A to B under the curve. So basically if I add this portion and add this portion, I can get the entire area, the entire blue region. I'm also going to call particular attention. I want you to see that if this is A, C, then it picks back up over here. This is C, B. So the link right here is these two values have to be the same. Okay, the C's, for it to have that flow, because that's their common point. So let's look at an example of this. Okay, so express as one integral. So my limit over here is negative 2 to 6 of f of x dx. I'm going to subtract lower limit from negative 2 to 2 f of x dx. But it says express as one integral. So I know these go together, but first of all, I want to, this guy does not match this guy. My c's do not match, so therefore it doesn't fit this theorem just yet. So we're going to have to use a property. How can I rewrite this? What if I flip some of these around? Right, so let's do that. Okay, when I pull a negative out here and then flip the lower limit and upper limit, I have this. Now I look and it's still not matching, but I see these two match, and it may help to just rewrite these. So I'm going to put this one on my left, so 2 negative 2 f of x dx, and this is just writing and rearranging so that it fits. I'm going to put this one on the right, so negative 2 6 f of x dx. Okay, now what about our c's now? Negative 2, negative 2. Our c's match. Now let's compare it to our formula. We have some number, our upper limit on the left term and our lower limit on the right term must be the same. Upper limit, negative 2, lower limit, negative 2. So we can now rewrite these, combine those, and we'll have a to b of f of x dx. No, that's not the only way you can do it. That's just a particular way. I went through it just so you can see some thought process through there. Okay, theorem 5.26 and corollary 5.27. This is just saying if our function is greater than or is equal to 0 for every x, then our integral is also, the antiderivative of this thing is also, the definite integral is also greater than or equal to 0. And this is just saying if your f of x function is greater than your g of x function, then the definite integral of f of x is going to be greater than or equal to the definite integral of your g of x. So take a few minutes to jot those down. Okay, verify the inequality without evaluating the integral. So we want to compare these two and show that this one's going to be less than or equal to this one. So write this one down and then we'll work this example. The first thing I did was I just sketched the graph of this 2x plus 2, which is and roughly that black line, which I didn't necessarily make it to that dot quite well, but 2x plus 2, and then the blue one is going to be the 3x plus 1. And we are asked to look at the interval from 1 to 4. So we can see from 1 to 4, the blue line is going to be greater than the black line for all values between 1 and 4 if we extended these graphs up. But also, let's just see that more clearly algebraically. So if I have 2x plus 2, let's evaluate at our lower limit, 1. Okay, then I want you to calculate it at 2 all the way to 4. So then at 3, and then at 4, and let's just point for point for point look at this. So we're evaluated at 1, 2, 3, and 4 because that's our limit. So from 1 to 4, and that's going to be 4. Then I get 2 times 2 is 4 plus 2 is 6, 8, 10. Now I'm going to pause it and do the same thing over to the left side, to the right hand side. Okay, now this is more work than we need it to do, but I wanted you to see graphically what that looks like, and I also wanted you to see algebraically. We can see that all the terms on the right, 4 is less than or equal to. In this case, it's the equal to, and then this one's greater, greater, greater than each of these values here. So verify the inequality without evaluating the integral. The textbook uses the graph more times than not, but I wanted you to also see the algebra side.